Hi, folks. Happy Monday. As promised, a quick recap, talk through the examples we looked at the end of class today. So as a reminder, today was our first day talking about rings and things. We define them and we are working to get on board with some of the vocabulary that describes these new to us algebraic objects. So I'm going to talk through these examples. So recall, rings are similar to groups, but now we've got two operations. We've got addition, we've got multiplication. Our set together with addition is necessarily, by definition, guaranteed to be an abelian group. However, with respect to multiplication, we don't have as many guarantees. So the questions we're going to try to answer about these rings include, first, is each ring commutative? Commutative means that multiplication specifically is commutative. You can rearrange the order. We're going to ask if a ring is an example of a ring with identity. Remember, we're guaranteed an additive identity. That's not a question or a qualifier, but the existence of a multiplicative identity is. Then we're going to ask about zero divisors. So rings are potentially kind of wild. We can have two non-zero elements that multiply together to give us zero. Yes, you heard that right. Zero divisors, two non-zero elements whose product is zero. Now, finally, we're going to try to collect some information on the units in our ring, where unit refers to those elements in our ring that do have a multiplicative inverse. Again, additive inverse, all set. We have that group structure under addition, nothing to check there. However, under multiplication, just as there's no guarantee that there even is a multiplicative identity, there's also no guarantee that a given element has a multiplicative inverse. So that's what we're going to explore through this series of examples. So our first example here is our prototypical example of a ring, that is the integers. We know and love the integers, and we know and love the operations of addition and multiplication over the integers. You can sort of think of the idea of a ring as trying to capture that structure in a general context. So, is this ring commutative? Yes, multiplication of integers is commutative. Is there an identity? Yes, indeed. In fact, we sort of borrow the notation of the integers throughout. We're going to say the multiplicative identity is 1, the integer. Are there zero divisors? No, you would have encountered zero divisors much earlier in your mathematical career if they existed in the integers, surely. And as for units, now this is why the integers are a great example of a ring and an okay but not fully realized example of a group, right? Under multiplication, the only elements in the integers that actually have an inverse are 1 and -1. For our next example, we consider just the even integers. Now, again, we do have a ring, right? Addition, multiplication, the distributive property, all legit and keep us contained inside the set of even integers. However, we're going to encounter some limitations. So multiplication is still commutative. Yes, indeed, this is a commutative ring. But no, we don't have a multiplicative identity. 1 is not an even integer. Similarly, no zero divisors, none in the integers, none in the even integers, and no units. Now, before we get too excited about checking if there are units, if we don't have a multiplicative identity, we can't have units. That would violate closure of our ring. So it's a non-starter there. All right, so for our next example, we're going to dive into the integers mod n, z mod nz. Once again, we're building a ring out of the integers, and so we maintain commutativity. This is indeed a commutative ring. And similarly, we have an identity element, a multiplicative identity, specifically the equivalence class that contains 1 functions as an identity in this ring. Okay, now where things get fun and interesting is when we start thinking about zero divisors. Because of this modular arithmetic, we have zero divisors in z mod nz. In particular, any integer that shares a common factor with n in Z mod nz, its equivalence class is a zero divisor. That element is a zero divisor in Z mod nz. On the flip side, if you look at an integer that is relatively prime to n, then you have yourself a unit. Any integer relatively prime to n, its equivalence class functions as a unit in the ring Z mod nz. So let's see if we can prove these last two statements. First, let's think about our zero divisors. While there aren't really two cases here, I think it's helpful to build our intuition by first thinking about the case where we've got an integer that divides n. So if d divides n, that means we can write n as the product of d and something else, let's say q, which in turn means that taken as equivalence classes, bracket d times bracket q is the same as bracket n, which in Z mod nz is 0. So clearly that divisor is a zero divisor. Now that I say that in words, that seems like it makes sense, right? It's a divisor of n, and when we mod out by n, we're essentially saying, hey, set n equal to the identity, set n equal to 0. Okay, now in the case where maybe we don't have strict divisibility, but we do have common factors, say the greatest common divisor of m and n is d in this case, again, we can write n as d times q, but we can also write m as d times s for some other s. So d times q, that makes a nice zero divisor pair, but m times q, now this is interesting, right? We're taking m and pairing it with the remainder of d when we divide that into n. M times q, well, we can replace m with d times s. We've got d times s times q, which commutativity playing a big role here. We can sort of regroup that d and the q and say, oh, that's n. So once again, we're in the equivalence class. That's multiples of n, which means we're in the zero equivalence class. Okay, the unit case. If the GCD of these things is 1, that's a Bezoos identity moment. We're excited. We knew this was coming. So we'll say there exists some A and B so that AM plus BN equals 1. And now just go through and mod out by n, right? Reduce mod n. A and m, that b times n becomes 0. The equivalence class containing 1 is what's left over. So we've got units. A and m in this case function as each other's multiplicative inverses. All right, our fourth example, we are looking at q adjoin root 2, the rationals adjoin the square root of 2. So this is all real numbers that look like a plus b times root 2 for a and b in the rational numbers. Yes, this is a commutative ring. Good news. In particular, we're dealing with real numbers, and they interact as real numbers should, so we sort of have that commutative property inherited. Similarly, we have an identity. This is a ring with an identity. If a is 1 and b is 0, you've got 1 in the form a plus b root 2. Are there zero divisors? No, in fact, there are not. Again, this comes down to the fact that we're looking at real numbers. We're sort of contained in real numbers. And then for this last question about what are the units? Well, surprise, q adjoin root 2 is a field. In particular, it's degree 2 extension over the rationals, which is a field. It's very exciting. Algebraic extensions, loving it. We're not going to get there in this class, sadly, but yeah, there's a whole lot we could study here. You should drop a comment if I'm wrong about the inverse, because I'm trusting my Monday at 10:30 at night brain, but I'm pretty sure that works out. So this is a field. Everything is a unit with the notable exception of 0, the additive identity. Next up, let's take a look at our real Hamilton quaternions. So as a reminder, these are linear combinations or sort of polynomials with real coefficients in the elements of the quaternion group. So we're looking at I, J, and K again, but now our elements in this ring look like A plus BI plus CJ plus DK. It's sort of this extended complex number set. Let's see. So is this commutative? No, no, no. This is our first favorite, coolest example of a non-commutative division ring. So in particular, I times j is not the same thing as j times I, and so assembling our elements as these combinations of those sort of basis elements or building blocks, yeah, we're toast. There's no way to cook up something commutative out of those non-commuting elements. Well, no non-trivial way. I'm getting off topic. Is there an identity, however? Yes, indeed. If we choose our coefficient a to be 1 and everything else to be 0, then we just get 1. Let's see. Are there 0 divisors? No, because part D, everything is a unit. Remember, an element cannot be both a 0 divisor and a unit. It can be neither, but it cannot be both. And this example we saw in class is a division ring. Everything has a multiplicative inverse. I'm going to skip past the details on that, but you can find videos from our class session where we've got some discussion on that. And at long last, we are ready to talk about perhaps the strangest example of the day. We're going to talk about the ring of continuous functions from R to R. So real valued input, real valued output, continuous in your traditional calculus, well-studied sense of continuity. We'll define addition here pointwise and multiplication pointwise. That is, at a given input value, your output is now defined based on the output of those two functions combined as real numbers, right? Those outputs are real numbers. Okay, so yes, it's commutative. F times G, G times F, all the same thing because we're defining multiplication in this pointwise way that exists in R. Is there a multiplicative identity? There is an identity function. F of x equals 1. Multiply by that all you want. Your output values, your function values do not change. Okay, 0 divisors. I'm not going to give you well, hopefully it's a satisfying answer, but I will not give you the full analysis treatment here. Let's just think about an example. Let's say I've got a function like the one pictured on the left that's 0 on the left half plane, right, for all input values that are negative, and some other function where all my input values, or sorry, all my outputs are 0 for positive inputs, right? These two functions, neither of them is the 0 function, neither of them is the additive identity. However, when we go through and multiply the outputs at each point, we got the 0 function. So that's an example of 0 divisors, right? If you've got a function that is 0 on some interval, then you've got a 0, its matching pair 0 divisor is any and every function that is 0 on the complement of that interval or that series of intervals. And we're not going to get into the open versus closed versus interval versus some other set of points. There's a lot we could get into here, right? The intersection or the interface between algebra and analysis in this way is just so rich, and there's so much to say, but I'm cutting it off there. Hopefully that is at least a little bit informative. Similarly, if we want to talk about units and multiplicative inverses, we're going to need a function that is 0 nowhere. So this is good. We seem to have set ourselves up to not have functions that are words. Yeah, we don't have any overlap between our 0 divisors and our units, right? Our 0 divisors must be 0 somewhere, and our units are those functions that are not 0 anywhere. And so if f of x is not 0, then we can let g of x be 1 over f of x, and our product is that multiplicative identity element of 1. Whew. Okay, that was fun, hopefully, for you as well as for me. Let me know if you've got questions, if there are more details we can talk through. There's so much to think about in here, but yeah, welcome to Rings.